Hi everyone. So we're static integration, and we'll talk to you about some mathematics that you can use today to make your lives much easier. And so I'll just start with a brief kind of background. So my name is Denis, and with me today we have actually Matt, Jerry now, Nicola, and Dave, and we'll kind of tag team it a bit. And the slides that I'm showing you right now, in hindsight, after watching these things, I realized that I've been speaking to business people for too long. And when you're in that mode, you have to explain something like formal verification to people that have never written a line of code, hence these slides. And the kind of hearing these great talks today helped me get back into the kind of technical frame of mind. But please excuse the kind of the level of, let's say, technical analysis on these days. But the basic idea is that if you think about different types of systems, whether we're talking about commercial jets or all these constant glitches that you're seeing today. So for example, NASDAQ a couple of days ago announced that they had a bug in their closing auction for 7 years that they just didn't know existed, right? So my background is up until 3 years ago, I was working in Deutsche Bank in something called Central Risk Trading Desk. And one of the things I was responsible for is making sure that a trading system that had at any point in time, billions of years of exposure out in the market couldn't have a glitch. And that could happen because the brain of it was implemented as about 10,000 lines of MATLAB code. So lots of things going in and lots of things going out. So very quickly to have a situation where you lose a lot of money, you get fired. So I spend most of my time thinking about edge cases. So, what's a possible input that would lead to something bad? And around that time, 2014, my best friend and roommate from college, Grant Passmore, co-founder of the company, he was doing a PhD, actually a postdoc research at Cambridge, and we realized that. Again, I apologize for the technical slides. We just put this together. It comes from a business deck. But basically, what we realized is the techniques that people use to make sure that autopilot systems are safe. And what I mean by that is you have to cover infinitely many possibilities, right? Those techniques from formal methods got to a point that they're mature enough that we can actually scale them to software development at large. So we're talking about things like finance, robotics, etc. So this is about 5 years ago, and we had this idea, and the idea was that people are going to be writing a lot more functional code. And again, when we try to explain it to business people, they ask what is functional programming, and then once we explained it to them, they thought we were crazy. So we started the company, we started working on on this product, Imandra, which we'll show you in a second. And a couple of years ago, actually maybe even a year ago, we saw that something called ReasonML came out of Facebook, and it was a big thing for us because we realized this is something that's getting much more traction. So even though we've been working in finance and robotics, luckily this community has formed, and we happily embraced it. And one of the things that we've done over the past couple of months is we've created an interface to ReasonML. So what we'll show you today allows you to really take these latest advances in formal verification. So automated induction, all of the type system stuff that you'll see in a second, SMT, etc., to make your lives much easier. And what I mean by that is anytime you write a piece of code and you want to make sure it does something, the traditional approach is you come up with a couple of test cases, right? Which everyone hates. You take courses on it. Anytime, even in React, I saw like 12 out of 12 is testing with jest or whatever it is, right? Because it's painful. Everyone hates it. What Imandra, our product, allows you to do is to write properties of your code at a high level, at the level that you think. So when you write something, you say, okay, when A happens, I expect B to always happen, right? When you're testing for these things, you have to come up with a few examples of that. And obviously, testing never tells you that something will always work. It just shows you few instances where it might break down. So this is the kind of the big idea behind a product Imandra, which you can try today. Literally try.imandra.ai. And what we will do today is give you a brief intro into it, which is going to be slightly kind of, I guess, OCaml-centric. And then we'll show you a game of tic-tac-toe, which will be implementing ReasonML and all the cool things you can actually do with Imandra.
So I'm going to quickly describe to you what Imandra is and how to use it and what the capabilities of Imandra are. We're just going to go quickly over some examples from this first notebook that we wrote. So Imandra is a couple of things. Imandra is a programming language, which is essentially OCaml. And it also is a reasoning engine that can reason about a purely functional subset of OCaml. Transitively, it can also reason about ReasonML code because it's just a different front end for the same AST. So if you look at this very, very simple example, couple of functions, they don't do a whole lot. It's just taking an input, an int value, and checking whether a certain range is satisfied and returning different values depending on different ranges. We input those functions to Imandra, and we can compute with those functions. So we can invoke the function g with a value of 5, and we get the result of applying the function. It's just your regular REPL. What is unique about Imandra is that it supports a couple of keywords that other languages don't. And a keyword that we support is verify. What verify does is it takes a specification and it tries to prove that specification for you. The interesting part of how Imandra works is that it doesn't do, if you're familiar with quick check, for example, or other forms of generative testing, Imandra doesn't do that. Imandra reasons about the code that you've written. It statically analyzes the code that you've written, and it's able to prove properties about all possible values that those functions or those properties that you wrote satisfy. So Imandra is a formal system, and in formal methods there's essentially 3 different classes of systems. There's automatic theorem provers, there's model checkers, and there's abstract interpreters. Abstract interpreters are kind of a way of verifying properties for a sufficiently correct approximation of a program. Model checking deals with exploring the entire state space of a program and testing properties for every possible branch of that program. The critical thing about model checking is that it only works for finite state systems. So you can't reason with model checking on a function like map, because map potentially takes an infinite list. It doesn't necessarily terminate. Automatic theorem proving is a different way, and it deals with proving properties from the ground up from a set of axioms and a set of inference rules. What Imandra is kind of a mix of automatic theorem proving and a form of bounded model checking. In this case, for example, when we say verify that for every x, the invocation of g of x is going to be less or equal of 122, Imandra can prove this by model checking, because the g function that we saw here only has 2 cases, right? It can only say whether x is bigger than 22, then it returns 9. If x is less than 22, then it just returns 100 plus x. Imandra doesn't need to reason about infinite space to verify that this gdx is less than equal to 122 holds. One very cool feature about Imandra that you're not going to find in many other formal systems is that it has first-class support for counterexamples. So when you try to prove a property that doesn't hold, so we try to prove for f that for any value of x, f of x is going to be different from 158, Imandra can tell you not only that this is not true, but it can also tell you a specific instance of x for which this property isn't true. So if we try to compute f with this counterexample, which is x equal to 69, then we're going to be able to see that f doesn't actually return true. Another very cool feature of Imandra is what we call state space decomposition. So when we invoke decompose on the function f, we get this graph of all the possible regions of state, which in the case of f are going to completely match with the if statements of f. But in the case of massively larger programs, this is going to be quite different. So for example, if you look at the region number 2, we're going to see that Imandra tells us that for every input to the function f where x is less than or equal to 99, then f is always going to return 100. If we look at a different region, we're going to see that if x is between 70 and 20, and it's not 22, then the result is going to be 29, and so on. And Imandra can figure out this without doing any computation at all. So it's not actually running your f function. It's just analyzing your code and figuring out properties about your code automatically. So I said before that Imandra does model checking for simple cases, but in the case of recursive functions, model checking just doesn't cut it. What Imandra does is it has very strong support for a style of proving that we call that's called induction. So induction is kind of you can kind of think of it as the dual of recursion. And the very cool thing about Imandra is that it can figure out how to induct on a function just based off of its definition. So we're just going to skip over the definition of PSD and sum, but essentially we're asking Imandra to verify that those two functions are essentially equivalent, so that if this PSD function applied to x returns true, that implies that the sum of all the elements on x is going to be bigger or equal to 0. Verifying this by induction, we can see that Imandra comes up with an induction scheme, and this phi symbol is what mathematicians use to essentially say the property that we're trying to verify. And what Imandra is telling us that to verify this statement, we need to prove it for phi of the empty list, and for the case where the rest of the list implies the property for the entirety of the list. The power of Imandra comes from being able to generate those induction schemes. And the final very cool property of Imandra is that everything that we can write in Imandra is guaranteed to be a function that terminates. So in Imandra, it's literally impossible to write a loop that doesn't terminate. Because Imandra is going to tell you, I can't prove that this function terminates. You're either going to help me to prove it, or you're just not going to be able to write this. This is incredibly powerful for correctness. And it's very, very powerful, even for people that are starting to learn computer programs. Just imagine, like, you guys are Reason developers. You understand the value of a type system. Imagine a type system who can statically figure out that your function is not going to terminate. That's an immense amount of power that's given to you. So yeah, this is a quick overview of all the features that Imandra has. Now Dave is going to show you an actual example of how to use them in real code.
Right, hi there. So yeah, as Nicholas said, I'm going to try and show you this code now, which is Reason code. And actually, the demos she showed you before were in a camel. And this model was originally written in a camel, and I used reformat to just convert it straight to Reason, which has been great. And it's a little model of tic-tac-toe or noughts and crosses. So we've got a game here. If you get 3 in a row, marks as 1. I'm sure you've seen that before. So we've got a kind of pure functional core to the model. And then I've got a little diagram here. So we've got a core of the model that was originally written in a camel, and then I've wrapped it in like a React layer. And that's what I'm presenting today. We're hoping in the future to be able to kind of write in a camel as well, a kind of pure reason layer as well. That, because when you're gluing components together, you inevitably kind of have some logic in the view layer. And so being able to kind of show, like for example here, I've got different buttons glued together logically. I'm sort of mapping view states like is the button disabled onto this internal logic layer. There's inevitably going to be some logic here. So the more we can kind of cover, the better. So that's the idea. So this is as thin as possible for now. And then inside the logic file, we've got the actual game logic. And this is building, so I'll just go to this screen here. So if I break this file, my build breaks, go back over here, and now it's fixed. So I'm going to start going through this, and yeah, as I said, Nicola wrote this, so you're kind of joining me on the journey of discovery of how it works. So I'm going to fire up Imandra over here. Okay, so we'll start loading the definitions in Reason into Imandra. So the type of the player, the square state, so whether or not it's an X is 0 or not filled in. We have the grid represented here as just the different letters A to I as the different numbers in the grid sort of in rows. Load that in, which move you're going to make mapping to the square on the grid. The state of the game, which is the grid state, and also who went last. So when at the start of the game, the last player is none, and from that point onwards, it's always some X or 0. And the status of the game, so whether it's in progress, someone's made a bad move, or won or tied. And the initial game here is just the empty grid. And I'm going to do something now just to kind of, so you can see here, it's due to the representation of the grid. You get this, like A to H, none. It's quite hard to see what's going on. So I'm just going to quickly load these guys in. So this is just to sort of help the output in Imandra down here. So we'll load that. And this guy. And I'm going to do install doc of grid. So now if I print initial game dot grid, it kind of prints a little board instead of the values, so it's a bit easier to see what's going on. And if I put another grid down, we get sort of visual representation of it. So I'll carry on with what I was doing. So I'll carry on loading the definitions in. So we've got initial player, the value of a particular like move on the grid. So it's just a sort of mapping between the variance and the part in the state. And then the first actual like bit of logic of the game is whether or not someone's winning. So I'm going to load that in. And then this is quite, so Nicola mentioned about finding counterexamples when a property can't be proved. I'm kind of doing the inverse here. So I want Imandra to find me an instance where we see a winning game. And purely from these definitions that I've loaded, it can, so cx.game.grid, it's generated this value where X is winning the game. And that's true because there's 3 in a row, and this is according to our definition of winning here, which is quite thin. But this is sort of one of the most basic functions. So we're going to start building on top of this, building around this, and like adding more of the logic to the game. So we should start seeing more boards that look a bit more realistic. So another function, other player. And this function will count how many moves are made by each player. which you could see might be quite key to getting more useful examples than we just saw. And then building up whether or not a grid is valid. In this version of tic-tac-toe, either player can go first, so we check that if X went last, then X has one more move than naught. Otherwise, naught has one more move than X. So we'll load that in. And again, let's take a look at what we've written. So I find this instance to be really useful for actually getting a feel for what your functions are doing. So let's get an instance of a valid grid. So we'll do cx.game.grid. And as Nicola mentioned, these values are first class back into the sort of session. So I can use the isValidGrid function on it. cx.game and cx.p. Oh no, just cx.game. No, I need the last player as well, cx.p. And it. Huh? Anyway, you can see that it's given me an error. I've done something wrong, and so it's worked out the types of the two things. So you can use these values in real time as I'm doing with printing them. So yeah, let's get a couple more instances. So let's try and get it to prove something that shouldn't be valid according to our logic. So in this case, we're saying get the move counts of a game that you've generated from the definitions that we've put in. And I want a game that's where the grid is valid according to the grid and the player, but we're 2 ahead. And in this case, it says it can't do it because we've kind of given it like contradiction. So we'll encode that as a verification statement, which is what Nicola mentioned. And we could kind of see these as like tests. So here we're saying make sure that for these properties, like it's not doing something stupid, and you don't have to kind of come up with a test case that's potentially arbitrary, potentially wrong. It's just saying for all inputs, it'll prove it for you. So we'll carry on building a few more layers around this. So we've got, before we had whether or not the grid was valid, now we have whether or not the game is valid. So we're checking some properties about winning and get an instance of a valid game. And this one's quite interesting. I'll skip the other two because you'll probably get the idea. But so we want a valid game where X is winning the game. And now we see that looks more like a real game now, which is cool. We'll add the other rule, tied game. Did I hit the right button there? Oh no. There we go. And a valid instance of a tied game. Tied games, the grid is always full. So let's just see what that looks like. cx.game.grid. The grid is full and no one seems to be winning. We'll add another function, isValidMove, play move. So we can play a move on the initial game here. This is just computing with the value that we've already entered. So we're saying when we play a move on the initial game at position A, we get this grid. So again, it's just normal computation here. And then the status of the game based on those winning and tie functions. And this will actually this is the function we actually call from Reason to play the game. So we'll do that as well. And then this is it's sort of a property that seems fairly reasonable. Like if we've got a valid game and we've got a valid move, then when we play a move on the game with the move, the game should be valid, if that makes sense. So let's put that in and see what happens. And it's actually found that that's not the case, which indicates that we probably have a bug in the whole thing. So let's have a look. So to figure out what's going on here, we'd probably run these functions. So we'd run isValidGame on our counter example. That's true. and so on and so on, and we could execute all the functions with the value it's found. I happen to know what the bug is in advance to save a bit of time. So I'm going to show you here. When I demoed it to you, I didn't show you the bug. So I can actually play this, and then it doesn't check if the square that you're moving on is empty. So I can actually override that. And if I go back over here, this is the condition I need. I'm going to sneak that in into here and comment that. And I'm just going to reload this back into Imandra with the new definition. Oh, thanks. So it doesn't let you override definitions that are already there by default, but I'm just going to change a setting that allows you to do that, just to stop you making mistakes. So that is like up to the user whether or not they want to be able to do that. So now I've turned that on, evaluate that, and this function at G, and let's try that final statement again. And now we see, after analysing all that stuff, it's proved, and that final property is true. So yeah, that's the kind of overall demo. I've got a couple of other things I want to mention at the end. So around Reason stuff, we're working on a Visual Studio Code extension. If anyone uses that for Reason, I know it seems to be quite popular in the community. And by default, if you load a Reason file in, our keywords like verify and stuff cause a syntax error. So we've got this mode where you can add these keywords, and the idea is here we'd be able to kind of have instances popping up on inline interactively, and verification statements with a big green tick as you go through your code and you're working on it a bit more interactively than the kind of REPL-based approach that I just showed you. And then, yeah, if you want to go and have a play around with it yourself, as Denis mentioned, we've got try Imandra. So the docs that Nicola was walking through is docs.imandra, and if you hit try, it'll launch into a notebook that you can edit these statements yourself and change the values and play around with. And I'm not actually on the Wi-Fi, but yeah, on try Imandra again, this is all in a camel, but if you create a new notebook from the sort of menu at the top, you can choose to use Reason syntax as well. So yeah, I think that's pretty much it.